Welcome back to this module on pipelining. In this lesson, I will describe a specific case of a data hazard known as load use data hazard. Unfortunately, forwarding cannot always save the day. There is a case where a result cannot be forwarded because it is available too late. To explain this situation, consider this example. First, we have a load that is executed like this and writes its result to register R1. Then we have an arbitrary instruction, in this case a subtract, which normally is executed in these cycles and uses the result of the preceding load instruction as indicated by the black arrow. The result of the load instruction, the data being loaded, is not available until the end of the fourth clock cycle, and then it is available in this pipeline register. It is needed by this ALU, however, at the beginning of that same cycle, the fourth clock cycle, as highlighted here. Unfortunately, we cannot forward back in time. So in this case, forwarding cannot come to rescue. Such a situation where a load instruction is immediately followed by an instruction that uses the data loaded is called a load use data hazard. How do we deal with load use data hazard? As always, different solutions are possible, but the solution I will describe now is to add hardware called the pipeline interlock to preserve the correct execution pattern. In general, a pipeline interlock detects the hazard and stalls the pipeline until the hazard is cleared. To explain how it works, consider this example here. As before, we have a load that writes to register R1, which is followed by a subtract that reads R1, which is followed by and or instructions that also read R1. Now execution has advanced by 3 cycles, and we have this situation. Now the pipeline interlock detects the load use data hazard and prevents the instructions after the load from advancing to the next pipeline stage. In other words, in the next clock cycle, the subtract and AND instructions repeat their pipeline stage. The subtract instruction repeats its instruction decode stage, in which also the register file is read, and the AND instruction repeats its instruction fetch stage. Then in the next cycle, all instructions can move on to their next pipeline stages, and the result of the load can be forwarded from the mem write back register to the execute stage of the subtract instruction, as indicated here by the green arrow. After that, the hazard is cleared and pipeline execution continues as usual. Such a stall is commonly called a bubble, since it floats through the pipeline, occupying time but performing no useful work. Actually, the first MIPS processor did not interlock, relying on the compiler to remove load use data hazards by reordering instructions. Some people even claim that MIPS is the acronym of microprocessor without interlocked pipeline stages. Others, however, claim that the name MIPS is a wink to the performance metric million instructions per second, which is also abbreviated as MIPS. Perhaps both claims are true. Let me now sketch the implementation of the hazard detection unit that detects the load use data hazard and stalls the pipeline. The hazard detection unit performs its function in the instruction decode stage, since it may have to stall the instruction currently in that stage as well as the one before. First, it detects the hazard. It does so by checking if the instruction currently in the execute stage, the IDX pipeline register, is a load, and its destination register given by the instruction field RT is equal to one of the source register of the instruction currently in the IFID pipeline register. These source registers are given by the instruction field RS and RT. This check corresponds to this Boolean expression here, expressed in C-like pseudocode. If the check succeeds, in other words, if the Boolean expression evaluates to true, then the hazard detection unit needs to stall the pipeline. It does so by preventing the program counter and the IFID pipeline register to be written. We can prevent these registers from being written by adding write signals to them and by clearing these write signals. This makes sure that the IF and ID stages are repeated for the same instructions in the next clock cycle. In addition, a NOP, a no operation, needs to be inserted into the pipeline starting at the execute stage, since the hardware is doing something in every cycle. This can be implemented by inserting the control signals for an instruction that does not write anything into the IDX pipeline register. Even though the pipeline interlocked, the hazard detection unit makes sure the hardware works correctly, we still lose a cycle and hence performance when a load-use data hazard occurs in the code. The compiler can and should avoid such performance penalties by scheduling the instructions in a way that load-use data hazards are avoided. To see how, consider this example. We want to produce fast code for the statements A becomes B plus C and D becomes E plus F. Here's how the straightforward, unoptimized code looks like. First, we load B into a register, let's say RB. This is not real MIPS assembly code, but a kind of pseudo-assembly code. In reality, RB should correspond to one of the MIPS registers, R1 to R31, and B should be replaced by the register containing the address of B. It is just to illustrate load use hazards. Then we load C into a register RC, and then we add RC to RB and write the result to RA. We see, as indicated by the red color, that there is a load use data hazard because the load to RC is immediately followed by an instruction that uses RC. Then we store RA to memory at the address indicated by A. Notice that there is a dependency between the add and store word instruction, but this dependency can be solved by forwarding. And finally, we translate the statement D becomes E plus F similarly, and see that there is a load use data hazard between the load to RF and the subtract instruction as indicated by the red font color. In order to eliminate the stall cycle between the load to register RC and the add, we need to find an independent instruction that can be moved between the load and the add. Do you see which instruction should be moved here? You have 5 seconds to find an answer. The first instruction that can be moved there is the load to register RE. This instruction is not dependent on any of the preceding instructions, so moving it up is legal. We also need to find an instruction to get rid of the stall cycle between the load to RF and the subtract instruction. Do you see which instruction should be moved there? You again have 5 seconds to find an answer. In this case, the instruction that should be moved between the load and its use is a preceding instruction, the store of register RA to address A. By moving it down, it stays behind the instruction on which it depends, the add instruction, so moving it down is also legal. This is how the final optimized code looks like. The load to register RE is moved between the load to RC and the use of RC, and the store of register RA is moved between the load to RF and the use of RF. In both cases, this is indicated by the green color. This completes this lesson. Thanks for watching. In the next lesson, I will describe control hazards, also known as branch hazards. Hope to see you back.